Well, welcome everybody to a session on building reconfigurable networks. We've got a lineup of 4 excellent papers exploring different ideas on how to do that. First up, we have Realizing RotorNet Towards Practical Microsecond Scale Optical Switching, and George Porter, who's a professor at UCSD working on network systems, is going to give us a talk about that. And as far as I know, he's not on the job market, but...
Always looking for students, for sure. So good morning, everyone. Thank you for inviting us to this really exciting session. As was mentioned, my name is George Porter at UC San Diego, and with my colleagues Max Mellette from inFocus Networks, Alex Forencich, Rukshani Athapathu, Alex Snoeren, and George Papen, we're excited to present some of this work to you. And all of the authors except for Max Mellette are here at the conference. Unfortunately, he wasn't able to travel to Sydney, so I'm going to be giving the talk kind of on his behalf. I want to talk about 3 sort of high-level trends in data center networking that you've seen a little bit during this presentation, during this conference. One is the driving of high bandwidth networks. So we've seen the introduction of accelerators like GPUs, TPUs, et cetera, that have been driving bandwidths inside of boxes and in between boxes at a dramatic pace that has been a challenge for network operators to address. We've also seen increased heterogeneity, both heterogeneity in terms of the types of devices that are put into networks, but also network speeds. For example, as you begin upgrading parts of your network, replacing components with other components, we end up with a heterogeneous set of capabilities that we have to support. And because the network is what's actually connecting all of our devices, the question arises, how do we do that? Do we build a new network every time to address the maximum requirements, the minimum requirements, or something in between? This is a huge cost and a driver of both capital and operational expense. Finally, what we're really seeing these days, especially in the last couple of years, has been increased workload specialization. So gone are the times of general purpose data center applications running on a smooth network. What we're seeing are tailored topologies such as toruses and other things driving specific workloads like AI and machine learning, et cetera. And in order to optimize those networks, it is sometimes the case that we want to change the size and configuration of those networks for that particular workload. Not to mention that unlike sort of classic data center applications, individual device failures can cascade and cause entire workloads to go offline. So this combination of high-level drivers has led to a motivation for wanting to introduce optical circuit switching into data center networks. And you've seen that in the research world, and you've seen that increasingly in deployment at large-scale hypervisors. I want to take just a quick second to define our terminology about what we mean when we talk about optical circuit switching. So this is an example of an optical circuit switch, which is a technology-dependent switching element that simply forwards light from one input port to an output port. So this type of device is not reading packet contents, it's not looking at packet headers, it is simply forwarding light from one port to another. As such, it requires a different approach for control. It's externally controlled, not internally controlled based on packet contents. And the ability to change the mapping, the matching from a particular input port to an output port is technology dependent, and it's defined by a system level metric we call the reconfiguration time. A benefit that we get in doing this, though, is that we do not need optical transceivers to convert between light and electronics. And in particular, these devices are bandwidth agnostic, meaning that as we upgrade those parts of the network with newer technology, newer devices, newer accelerators, we can amortize this switch across multiple generations of devices, saving capital, operational costs, carbon footprint, et cetera. And so there's real benefit for doing this. We're seeing this in industry, as I mentioned. So Google has been publishing work in this space, for example. Other providers have been doing this as well. But at last year's SIGCOMM', we saw this design for an optical circuit switching framework that allows different parts of the network to be directly connected through these OCSs. And in the middle, you see a picture of that switch. And embedded in that device is a MEMS microelectronic mirror component that actually implements this optical circuit switch. This is an analog device that can reconfigure at a scale of milliseconds. So these examples, the example I just showed is what you might call slow switching, in the sense that it is suitable for changing topologies in between jobs. The end-to-end reconfiguration time of a technology like this might be seconds to minutes to hours or longer. And this means that when we deploy a large-scale job, we can customize the network, we can respond to failures, and we can implement this in between these different jobs. But one question we might want to ask is there a benefit if we could adjust the topology of the network within a job's runtime? So as the communication behavior changes within a job, can we actually track that communication behavior change? And can we, for example, find a phase of the application's performance where we need to connect compute to, let's say, non-volatile storage? Or do we need to connect a storage accelerator or a compute accelerator at a different phase of computation? And that's something that we're really quite interested in. This has the potential to increase efficiency, lower costs, lower energy, et cetera, if we're able to achieve that. Now, we are not the only ones looking into this. This has actually become a really important source of research, and you've seen research over the past decade and longer, actually several decades, and there's a number of examples in our paper that I would draw your attention to, and there has been more contemporary work as well, and in fact, this session is a great example of some other projects that are looking into aspects of reconfiguring the network for various purposes. So if we want to move from slow to fast switching, you might just say, well, let's just make our switch faster, right? So that's something that we're kind of interested in doing. And so what we've been focusing a little bit on is how to do that at a practical scale. So we're building upon a particular design that we proposed at SIGCOMM'17 and then further refined at NSDI-20 that was a design based on a so-called oblivious control plane, meaning the network is not responding dynamically to traffic changes. It is simply implementing a particular connectivity that the endpoints will respond to. We can support low latency packet transmission through a mechanism based on multipath and expander graphs that's defined in the paper. But when we described and built these systems in 2017 and 2020, the actual prototype that we built was built with an example of that slow optical circuit switch, essentially the same technology as that Google Palomar switch. So what this paper is actually doing is keeping that oblivious control plane. We've implemented and validated that low latency protocol that we call Opera, and we have developed and built a new type of a non-MEMS rotor switch OCS device. So we built a new kind of a switching element, and we designed that element to work with commodity optics and data center environments. And so this paper is really about our experiences building that network and the lessons we learned along the way. Now you may ask, why did you build a new type of switch? We could just make the old switch go faster. So, why don't we just put more energy in it or kick it really hard and tell it to go faster? And there's some fundamental reasons why we actually can't do that. So current OCS MEMS designs, it's very difficult to make them both simultaneously faster, but keep the radix high enough to be relevant for data center scales. So if you kind of zoom into that Palomar switch that I showed a couple slides ago, fundamentally that device is an analog device with small mirrors that have to steer light from one place to another. Now, if we have a small number of ports, we can make very small mirrors, we can move them very fast. So this gives us fast reconfiguration time, but low radix. As we increase that radix, we have to make that memory element bigger, the mirror element bigger, and it slows us down. So we have this tension between radix, the port count, and the reconfiguration speed. And I do want to point out there are research technologies that are very fast in terms of reconfiguration time, but are either low port count, or they require new types of optical network technology that's not compatible with kind of current data center designs. And given that optics can be a very significant part of data center network costs, we wanted to optimize our design for commodity optics. So we're faced with this device level limitation where we want to have high radix but slow switching time. And I want to point out that this is not, this problem that we're running into is not unique to networking. It's often the case that we have system level targets that we're trying to hit where the device that we use to implement that system cannot actually meet that target. So imagine a storage example where we have a petabyte that we want to implement. certain IOPS, certain reliability, et cetera. And we go and we look for devices that might make up that system, and we see that there's a huge gap. In this case, we have a hard drive with a particular capacity, speed, IOPS, et cetera. There's a huge gap between those two things. Now, we could try to make that device better. We could add more platters, more spindles, more disk arms, et cetera, but there's going to be a huge engineering challenge with limited kind of payback. So what do we end up doing? We end up building, in this case, storage arrays. What we end up doing in the storage example is spreading data across many devices using replication and coding theory, geographic distribution, et cetera. And so what we end up with is a system that's able to realize certain properties, even though the actual device that we use is unable to actually deliver that property. And this is common in computer science, computer systems design, and we see this in a lot of different examples. We're just going to be taking that same exact principle, but applying it to the network interconnect for this project. To explain a little bit more what I mean by that, we have proposed and built this non-crossbar switching element that kind of forms the basis of this RotorNet design. Now, that Palomar switch example and other examples of using these so-called 3D MEMS switch devices implement what's called a crossbar switching model, meaning that traffic arriving on any input port can be forwarded to arbitrary output ports, meaning that that switching element is required to implement every possible input-output matching that we might need at a network level. There's n factorial of those matchings, which adds a lot of cost and complexity, and we ran into that issue with those steerable mirrors. Remember, we're trying to steer that mirror to any one of our possible output paths, and that was the roadblock at the device level that led to this limitation. What we're implementing is a non-crossbar element, which is only able to steer traffic in a very fixed and limited way from input ports to a subset of the output ports. This gives us the very basic amount of connectivity necessary to bridge traffic from input ports to output ports without the ability to arbitrarily connect them. So we're restricting the features of our switch, and we're going to be recovering this crossbar switching model at a systems level, at a network level, but not at the device level. To kind of show you what I mean by that in a very brief way, imagine that we have a small 16-node network, and in order to, if we were to implement that with the crossbar switching element, we'd have to have that device implement n factorial matchings, in this case 16 factorial matchings, in some arbitrary sequence. Instead, imagine that we only had 16 of these matchings. And in fact, imagine that we spread those 16 matchings across, in this case, 4 switches. So what you see here on the right is the fact that we have 4 switches, each with 4 of these matchings, so that's 16 matches in total. And if you look at these connectivity patterns, what you see is that none of these actually implement all-to-all switching. But if you were to send traffic through the network multiple times, you could transitively go from any input port to any output port. This allows us to build a simpler model. Okay. So I want to talk about a couple of the quick things very quickly about what we ended up doing. So on the left, what you see here is a diagram of the switch that we built. Traffic ports come into this device. They are projected onto a spindle that implements these small set of matchings in this cyclic way. And on the right, what you see is that deployed in a rack at our lab at UC San Diego. Now, we needed to be able to make this on the budget of a university. We don't have kind of Google or Microsoft scale resources to do this. And so I want to talk about a couple of the implications that that led to. So the first was to actually build that spindle. What we ended up doing is we took a hard drive that we had apart, we patterned the face with gold, and we ended up creating these diffractive disk sectors using a very low-cost technique that involves laser etching. And so we were able to implement each of these matchings on that disk with very low cost. Now, one of the things that came out of that, though, was that even though this process is very inexpensive, it led to these little point defects. And it's very similar if you're old like me and you ever listen to an audio CD that skipped, that's exactly what's kind of happening in this case. So we were curious about whether we could, what the effect that would have on network performance. Another implication was that even though these disks are cheap to manufacture, we need several of them in the middle of the network. And so rather than make n different disks, we can simply take a single disk and permute the way we connect it with fibers in order to stamp those disks out in batches, which is, again, similar to how audio CDs are made and saves money as well. We wanted to be able to support commodity end hosts and end host protocols. And so this is kind of a pictorial diagram of all the different components that we have in our system. We have an FPGA NIC based on the Corundum platform developed by Alex Forencich, who's somewhere in the back here. And the thing that was useful about this is that rather than having to control packet transmission at nanosecond or microsecond timescales, which is very difficult, we simply cycle in flow rules, which is a lot more scalable. And the question we had from an evaluation point of view was, what is this going to do to the latency of our network, and can we implement low latency networking? Okay, I've obviously skipped a lot of details in the paper. I want to give you 2 quick examples of the evaluation, and then I'll conclude. So we care about throughput, we care about latency. We implemented this network on the right, so you can see kind of a picture of this. We have a 128-port bidirectional rotor switch divided into 4 networks, and we have 16 hosts that are implementing. Each has 2 Corundum NICs in it, and so we have 32 hosts. We went ahead and evaluated TCP performance, and what we saw was that there was a real gap due to those point defects. It caused packet loss, and it reduced our TCP performance. So rather than using a more expensive manufacturing technology to build a better disk without any point defects on it, what we were able to do was to have that Corundum NIC scan the disk and detect those point defects and remember them. And then what we can do is essentially delay packet transmission during the times that those point defects exist, essentially creating a lossless network at the cost of a small amount of bandwidth due to the fact that we're not transmitting all the time. And if you look at the evaluation, what you can see is that that drove link utilization up close to 100% in this particular case by skipping those point defects. Now, what about latency? What you see here are 2 CDFs that represent on the left kernel-to-kernel ping time, and on the right application-level UDP performance similar to, for example, RPC calls. And we compare our low-latency Opera protocol, both loaded and unloaded network, compared to a ConnectX-5 NIC, either going through a packet switch or back-to-back. And the sort of takeaway here is that we have comparable latency to our packet switch baseline, which is great news. We have somewhat worse 90th percentile latency, in part because we're sending that packet through the network multiple times, which you don't do in a packet switch network. And we have slightly better latency above the 99th percentile, which we're attributing to somewhat different batching behavior in the Corundum NIC versus the ConnectX-5. So with that, I'd like to conclude. So we've demonstrated a practical path to implement a rotor-like optical network at scale. We built this 128-port bidirectional optical rotor switch, developed supporting NIC hardware and host software. Those are open source through Corundum. And it works with commodity optics, which we felt was really important given the high cost of optics in the data center. We have a real-world evaluation of Linux TCP throughput, standard protocols, and host-to-host latency. And I think the main takeaway we want to leave you with is just the fact that we were able to build this network because we chose this alternative switching element, and that choice really cascaded down to simplify the design of the rest of our system. And so because we had a much simpler systems design, we were able to kind of build the system. So with that, I'd like to thank you for your time, and I'd like to thank my co-authors and open the floor up to questions.
Folks are lining up even before. Go ahead, please.
Hello, very nice talk. Yiting Xia from Max Planck Institute for Informatics. So could you elaborate a bit more on the host implementation? Like how accurate do you need to pre-profile these hardware artifacts, and how do you delay the packets, and how much do you need to delay them?
Yeah, that's a great question. So the question was about how do we sort of profile these point defects and synchronize those with the network, is that right? Well, so we're synchronizing the switch with the end host using the precision time protocol. And in terms of the implementation of the delay, like I said, Alex Forencich would be the expert on this, but essentially there is a series of forwarding tables that get cycled through in synchronization with the switch. We've layered on top of that essentially what is a mask, where you have, think of it as a bit field where you have the bits are particular lengths of time, maybe 1.5 microseconds or something like that. And whenever you have these dropouts, what we end up doing is taking one or more contiguous segments of that delay, and we just don't send packets during that time frame. So we're going to hold on to that packet inside the NIC before we transmit it.
And I suppose smart NICs now they support that?
Corundum supports that. It has to reach into the RAM. That's really important. I don't want to say that other SmartNIC platforms can't do that, but I know that Corundum, which is an open source platform, is able to do that.
Okay, thank you.
Thank you very much.
Hi, I'm Matthew Grosvenor from Jump Trading, but also formerly Exablaze, which was a manufacturer of layer 1 switches. Firstly, this is utterly heroic engineering, this disk and focusing lasers, and that's just mind-blowingly cool. So, like, hats off for doing that. But there are many existing electrical crossbar layer 1 devices in the market being used by various companies. I'm curious, a lot of the engineering you've done seems to apply to your fancy optical thing, but could also be applied to the layer 1 switches. Have you considered evaluating that? Have you done any work in that? Why choose the optics over the existing electrical devices?
Okay, so yeah, thank you very much for that. That's and all of the engineering, please, Max Mellette, Rukshani, and Alex deserve the credit for that, among some others. But to answer your question, we have looked at electrical crossbars, and in fact, we built a prototype earlier called Mordia that, reactor that was based on a switch from Mindspeed, and so we have looked at those quite a bit. A lot of the techniques could apply. One of the things about these electrical circuit switches is that you do have to retime and synchronize at the sort of physical layer, the performance, and so the devices that we've used have been fixed speed devices, meaning that if we do end up in that heterogeneous case where we're upgrading components, pulling out a rack, putting in a better rack with better speed or whatever, we're back into that sort of conundrum of having to either upgrade those or replace those at the same cycle and in the same cadence that we're replacing our hardware. And one of the things we like about transparent optical devices is we can decouple the upgrade cycle of our network with our devices. And so given that the fiber plant in a data center may last 20 years, we would generally like our network to last 20 years and be able to kind of cycle out hardware at whatever speed we're able to, I guess, is kind of our thought on that. But yeah, I think a lot of the techniques could be applied to both. Thank you very much.
Is it quick?
Very quick.
Okay.
Federico De Marchi, Max Planck Institute for Informatics. At what line rate were you able to run the actual testbed implementation?
Yeah, thank you. So all of the results I presented today were done at 10 gigabits a second. We also implemented everything at 25 gigabits a second, and it all worked except I think that not 100% of the ports were able to be supported due to some transceiver issues. And so we ended up with something like 80-ish% of our ports functioning at 25 gigs. So we only actually reported everything at 10 gig, and we kind of withheld the 25 gig results because we didn't have 100% success rate on that.
Thank you.
All right. Let's thank George. Thank you.